Today we are going to talk about energy efficiency, a topic that is transforming the industry, especially in the oil and gas sector. Companies are tightening their control over costs and evaluating new ways to improve efficiency. In refineries, petrochemical and fertilizer plants, process trains of rotating machines, such as compressors, blowers or pumps, are an important area to achieve optimization. Potential of this efficiency process. In this context, I will talk about replacing steam turbines and gas turbines by high-speed electrical systems, their impacts and opportunities. Some figures on CO2 abatement costs in the sector. They invite you to leave your comments or experience and knowledge on this topic and much more. This is a movement driven by energy efficiency, reduction of operating costs and sustainability goals. Our goal is to understand why this transition is happening, how it is planned and executed and the benefits it offers. Compared to traditional steam turbines or traditional gas turbines, are our centuries-old steam turbines on their last legs? Let's find out. First of all, welcome to the TURBIVAP channel, a channel about steam turbines and power cogeneration. If you are new here, nice to meet you. My name is Ronaldo Pex. I am a steam turbine specialist and here we talk about all of this. Visit our website and learn more about our products and services for turbo machines and also our courses focused on thermoelectric plants. The link will be here in the video description. Steam turbines and gas has been the heart of industrial plants for decades, driving centrifugal compressors and applications such as pipeline compression, refrigeration and LNG processes with powers ranging from a few kilowatts up to 100 megawatts. Gas turbines are divided into aeroderivatives and heavy-duty. They operate by burning fuel in a combustion cycle, while steam turbines use the Rankine cycle, taking advantage of steam from boilers or industrial processes. Although robust ones are being improved, optimize their efficiencies, turbines face increasing challenges, such as stricter environmental regulations, carbon taxes, increased operating costs, and the need for greater availability and efficiency. When these machines age or no longer meet modern demands, replacing them with electrical systems appears as a strategic solution. Why this pressure for change? First, emissions. A simple gas turbine. It emits about half a kilo of CO2 per kilowatt hour, which for an 8 mega compressor operating 8,000 hours per year results in 32,000 tons of CO2 annually. Steam turbines, although without direct combustion, depend on boilers that often in these industries burn fossil fuels, generating indirect emissions according to energy efficiency. Conceptually, aeroderivative gas turbines. They reach up to 40% efficiency under ideal conditions, while heavy-duty vehicles are around 27%, combined with an 83% efficient compressor. The powertrain reaches a maximum efficiency of 35%. Electrical systems with transformers, converters and motors can reach 80% total efficiency, with a jump quite significant for condensing steam turbines. Additional work is required due to lost heat in the condensation of the steam coming out of the turbines. The efficiency of larger turbines, such as the condensing turbine of the gas compressor, for example, is assumed to be around 80%. Smaller back pressure turbines for pumps and small compressors are assumed to be varying widely from 50 to 70% efficient. Additionally, turbines have operational limitations. Its speed range is restricted from 50 to 100% of the nominal power, with slow response and requires intensive maintenance, annual reviews and major overhauls, then every 6 to 9 years, which can add up to 140 days on average, or 100,000 hours of machine downtime. The startup time of these machines is average, quite rough, and up to 15 minutes. And cooling also impacts flexibility. All these factors added to the wear of components, such as sealing, the blades, bearings, they reduce reliability of old fleets, making modernization an urgent need. Not to mention all the other peripherals involved in the process. The electric powertrain consists of a drive transformer, frequency converter and electric motor. It offers a different approach. It allows variable speed control, which can go from 25% to 120% of the nominal power, delivering only the energy needed by the compressor, which is ideal for dynamic processes such as gas fields, where the suction pressure decreases over time. So high-speed motors, they eliminate the reducers, reducing mechanical losses and simplifying design. While technologies such as magnetic bearings, solid shafts tested with over-rotation, they guarantee stability without field adjustments. Installation was generally designed to be plug-and-play, with fast commissioning. So, these engines can be ready in a day, and the engine starts in less than 4 minutes there, against the long heating cycles of the turbines. Although again, many of them already have some device features to increase starting time, cooling time with devices quite advanced and yet still take longer, obviously, than an instant starter. The compact footprint of high-speed motors. It fits in well there. The foundations of the turbines, often a custom base plate. Then a customization is made and this entire kit and set is elevated and positioned on top of the civil constructions of typical process turbines. It is obvious that a complete study must be done behind the scenes. Okay, but is it totally possible or is it 95% efficient? In this type of powertrain, combined with minimal maintenance, annual visual inspections, and reviews every 4 or 5 years for the typical industrial shutdowns, eliminating the need for extensive overhaul for up to 25 years on average, the lifetime of a typical turbine. And then replacing turbines in existing plants is more complex than in new implementation projects, as it involves adapting the foundations there and the compressors and the pre-existing infrastructures. The process begins with a feasibility analysis, can take a long time, even up to 3 years on average, mapping power, speed, space available and conditions of the entire electrical grid involved. So, 3 scenarios are common in this case: installing the electric motor, a new compressor designed directly by O&M for existing foundation. The second case is to refurbish the current compressor, adapting to the engine with an intermediate plate is what I mentioned. And third, keeping the compressor intact, requiring a dynamic analysis. Detailed reverse engineering to ensure compatibility. The foundation is the central challenge in this steam. It has specific weight distribution and spacing, while conventional electric motors may require different structural reinforcements. So, in our case, a typical house, we will have the turbine on the upper floor, the entire condenser part below, the distance. When we have generator reducer, then that's it. There is a very specific project to be done. Engines, the electrification of that. We have to see, analyze this structure dynamically, do seismic stress work there to see if it is possible to accommodate an engine there. High-speed engines, they have a reduced weight and compact design, minimizing these adaptations. Then, the removal of the steam or gas pipes and the installation of the infrastructure. High voltage, they must be completed in short maintenance windows, requiring coordination between experts, the manufacturers, the operators of these uncoupled and coupled. They will check vibrations and temperature, while torsional analyses can ensure that electrical excitations, like short circuits, they do not compromise the system. This is obviously done with the turbine design, but when we change to an engine, we have to redo all that. Integration. The control system is also critical. A high-speed engine, it must be configured to communicate with these existing systems, demanding expertise there. At the interface between new and legacy steam turbine technologies, network studies assess harmonic capacity and protection, and how much the steam balance or the connection to the power grid are adjusted to make up for the loss of local generation from turbines to the process. Because many processes are still dependent on turbine steam. Compared to turbines, the electric system offers very clear advantages in emissions. It is locally neutral and with renewable energy eliminates carbon impact. The gain will depend on the hand of the matrix used at 95% efficiency. The electric powertrain easily outperforms the 33% average of turbines, reducing energy consumption. So in the practical case of an 8 compressor mega that I started this video here, the demand may even fall from 180 to 300 gigawatt hours per year for about 30% less. It is reliability, reaching 99.9%. With these redundant high-speed motors and fewer parts, mobile, against 98% of 98 series turbines, with the reliability of a turbine while availability. She maximizes buy down, reduced teams and digital monitoring, perhaps even easier than steam turbines. Operationally, The noise is also completely lower. Then I will leave a table that at the end. We'll see how to approach this a little more. A simplified table, oil parts 2 and peripherals. All of this will translate economically. Initial capital may be high, but OPEX may be lower. In energy, maintenance, emissions and the possibility to sell unburned gas in pipelines, for example. Accelerate this process. ROI and return on investment. This chart is taken from the OGCI report. Is a marginal abatement cost curve, which illustrates the cost of abatement of CO2 emissions, based on the amount of CO2 saved annually. For different technologies applied to a highly complex scenario. The technologies listed from left to right are condensing turbine, electric boiler, electric waste heaters, among others. As we can see, a steam turbine technology at the bottom left of the graph, indicating that it is the cheapest option with the lowest potential for reducing emissions. It has a write-off cost of around $100 per ton of CO2 equivalent. Other technologies, as we move to the right, they present greater potential emissions reduction, but with significantly higher abatement costs. The condensing turbine is the most economical technology to reduce CO2 emissions. In this scenario, with a cost of abatement of approximately $100 per ton of CO2 equivalent. This means that for every ton of CO2, which ceases to be emitted when implementing this technology, the cost is relatively low compared to the alternatives. However, its reduction potential is limited. This positions her as an initial or short-term solution for companies looking to reduce emissions without major investments in real projects. High-speed motors, they already operate in applications up to 15 megawatts, with increasing demand for 25 to 35 megawatts, typical of petrochemical turbines, already proving the maturity of the technology and the technical and financial viability of this type of replacement. But every turbine can, or should, be replaced. Electric drive technology is readily available to replace steam turbines, up to 100 megawatts and capacity, potentially simplifying the startup and shutdown procedure and removing the inefficiency.